So, welcome everyone, and my name is Andrei Zlate-Podani, and I'll be speaking about integral types. We have been programming computers for a long time now, and roughly half a century ago, there was this idea that we need to do it in a more systematic way. And there was this conference in Germany where the participants actually identified a number of problem areas in developing software. And if we look at this list, we cannot say that we are today able to remove any of the items in there, right? And it's actually worse, because we would need to add some items like security or privacy. Now, coming to the subject of integer arithmetic and related, we can easily see that we still have problems, even in major projects like the Linux kernel or OpenSSL, right? And the problem is that when you are writing software, you are mostly doing it in a bottom-up way, where you write some instructions, call some functions, and hopefully handle some errors. In all these steps that you are doing, you actually have to observe the preconditions of various operations that you are doing. Otherwise, you normally land in the undefined behavior. And if you do not deal with errors correctly, this could also lead to undesired results. The C++ language has a wide number of types which are considered integers. But as we see, for example, for the bool type, if you actually use it in an integral context, your results will be incorrect. And actually, bool should not be used as an integer. This was a defect in the standard. And reading the standard carefully, you will see different places where they will explicitly exclude bool from various functions. Now, characters are a different beast. They are normally numbers, but the numbers do not have any meaning unless you actually associate it with an encoding. On top of that, we have 4 different character types and 2 bonus types, which is the signed char and an unsigned char. Those are just to confuse people. The white char type is implementation defined in size and sign, and is different than the char 16T and char 32T, which are actually not required to be 16-bit in size or 32-bit in size. They have to be at least those sizes, right? If we are thinking about the most widely used character encoding types today, the Unicode standard is the one to use, and it has an additional complexity that for one a glyph, which would be the graphical representation of a character, you can have n different character sequences which can represent it. And this creates some challenges for comparisons, for example. You cannot blindly compare byte for byte Unicode strings and expect to get the correct result. Now, in the Boost library, you have various libraries, and one of them is the property tree. And the property tree has the option to parse XML strings. This particular piece of code is trying to recognize a character reference in the hexadecimal format. As you see in the second comment, this is the string that is trying to recognize, and the maximum value which should be accepted. Note the first comment, which says assumes ASCII. Well, XML files and strings in general can have various encodings, but this assumes ASCII should basically ring all the bells for anyone reading this code, because this would be a precondition for the code, right? Now, this is where it gets interesting. So they are trying to read one of those hex digits from the string. But they would just chop off 8-bit from whatever is in there, because this whole code is actually part of a template class. Okay? And the template class is using a character as a template type. And characters could be chars, could be Y chars, could be char 16s, and so on. And not only that they are chopping 8 bits of those, they are trying to recognize them using a table as a digit, right? This obviously doesn't work for the wide characters. Moving on, we have a code which is then trying to calculate the code point for that particular sequence. And there's no check for overflow, no a restriction on the maximum value accepted here, which then whatever value is computed in there is passed to this particular function, which is another template function which takes some flex parameter. Now, those flex parameter will ask the function to convert that code point either as a ASCII value or UTF-8. Doesn't matter which character type you actually have for the encoding for the enclosing class, right? And of course, you will get the wrong result if you are using this parser with Y chars. And this is actually a problem that is quite difficult for many implementations where you have 4 different types combined with 3 different kind of encodings, and you are trying to juggle the transformation from one encoding to a different one correctly. Moving on to integers, finally, the signed integers are special in that they do not behave as their mathematical counterparts. If any operation you are performing is prone to overflow, then the result is undefined. So a lot of the properties of the operations are not defined for the whole range of integers. Now, C++ also has the special rule that smaller types will be promoted to an integer type when you are doing computations, right? And if we look closely, we notice that because of the integral promotion, you get you could get different results depending on the white space which you use in your code. And this is, in a way, counterintuitive. And you actually may not know when you are doing a refactoring which of the results is desirable, unless you have some kind of tests. The Boost accumulators is a library, a sub-library inside of Boost, which is providing some statistical functions which can be applied to a set of values. And this is basically the example directly from the user's guide. And we could see that we are adding some integers, and then we will extract the sum of those integers and the mean back. All good so far. But then we are wondering what can happen, how is the overflow handled by this library? And we consult the user's guide. There's no indication in there, which is generally a bad sign. Reference, I'm not expecting you to read this, but it's actually just information from the headers. So we will do a test, right? What happens if we overflow? And obviously we get the wrong result for the sum, but more importantly, we get the wrong result for the mean, which means that you get a cascading effect. So you have an error in one place of the code, which reflects in the end in some other place, which is completely unrelated to the original one, right? The accumulator library actually has two ways of calculating the mean. One is the lazy one, which I was showing earlier, and the second one is the immediate. The immediate will try to compute the value as they are pushed into the accumulator, and it will, in this case, show the correct result. Now, digging a little bit into the source code of Boost accumulators, I got this class which actually implements the sum, and the author actually considered that if you are using some integral type in there, you might overflow. But then he just said, yeah, this can happen in real life. So just continue. Now, the same or similar attitude is actually to be found in the standard library. And I think this is problematic. So in this example, I have this the least common multiple function added to C++17. It has a precondition that the result will fit. For LCM, it's actually quite easy to get large numbers. As long as the two numbers have the GCD equal to 1, LCM will return the product of the two. And for this example, you have two small numbers, and the product is over 4 billion. Moving on, so at least LCM was having a precondition informing you that if you do not fit in the resulting type, you will basically be in undefined behavior. But the accumulate function doesn't say anything, right? So, and you are doing operations on a range, possibly large. So it's quite possible that you will have some problems at the limits. Now, the accumulate, what's interesting about it is that theoretically, it has enough information to provide you the correct result if there is one, and it can fit in the resulting type. But the way it is defined right now, it will just go in sequence through the elements. There are other functions which were added recently to the standard, which have the same way of defining their behavior. They take a range, and they do some operations, and whatever comes out is your result, and whatever that might be. Now, this is sad in a way, because the processor does it for you for free. So you only need to add to the standard library the possibility to perform certain operations which would return the correct result of your operations, such as addition and subtraction. These are examples of branch-free implementations, how you would detect overflows in these two operations. I have underlined the place where the operation is actually performed, so you could have versions which would return the result as well as the flag if you have an overflow or not. Now, these particular functions, if you are implementing them in C or C++, they will translate to something like 7 to 10 assembly instructions in the x86 instruction set, which is quite a lot. But the equivalent in an optimized fashion would require something between 3 and 4 instructions. So roughly the half of the cost of implementing them in code. And if you have this optimized version, you could, for example, implement a version of accumulate which could detect the error without actually having any measurable performance impact. Superscalar execution and all that generally helps this. But please note the part where I have marked that there is no branch in the loop itself, right? The branch is only afterwards, because you are not interested in the result when something goes wrong, but just to detect that something went wrong, right? You can also detect overflow for multiplication. It's slightly more complicated than for addition. On the left side, we have it's actually the unsigned version. Also, the parameters are written incorrectly. And on the right side is the signed version, I think. And multiplication actually is good to have in two versions. So one which would detect the overflow, and the other one which would give you the result as a double word. This can be very useful if you are trying to write, for example, a multi-precision library, because then you could, in a portable way and with good performance characteristics, you could implement whatever level of precision you need just by having this support. The same is true for addition. So for addition, the overflow flag is actually also the carry bit. So you could, in theory, implement multi-precision using this information. For the signed version, you obviously need to make sure that you extend the sign as needed. detection of division overflow is actually quite straightforward. Mostly just don't do division by 0. But you can also have an example of double word division by word to get a double word and remainder. And this is actually very complicated to implement in code. But the part in the middle is actually the one which does the heavy lifting. And we have more code. This is the complete working code of performing long division using C++. While I was investigating the usage of integers in various scenarios, I was thinking, what are the Haskell guys doing? They have this idea that when they write code and it compiles, it's most likely correct. And this is an excerpt from the they call it a language report. It's from 2010. It's equivalent of our standard. And at the top, they have a very nice a paragraph where it says that they didn't use floating point compatible with IEEE floating point arithmetic because it was too complex for their library. This means that basically Haskell code is not necessarily portable between machines. Now, the integers are also interesting because, first of all, they are not fixed size. The size is implementation defined, and it's at least 30 bits which they can hold. 30 bits, that's quite an interesting number. And the result of overflowing mathematical operations is, in our parlance, implementation defined. So some compilers could choose to detect it. Some could return all kinds of other results, such as a truncated value or special value. So I believe this is a sign that integers are actually difficult to understand for everyone. As I've already mentioned, having such primitive functions in the standard library implemented in a way which is optimal for whatever target machine you are compiling for would actually help in not only writing correct code, but also code which performs well. Now, I have this point there about abstracting away essential details. This is, if thinking back at accumulate actually takes integers and takes floats and takes strings and whatever. And the semantics of the plus operator for integers is not the same as the plus for floats or for something else. So in a way, the result is not well defined, because you cannot mix apples and oranges and expect that you will have something which is unitary. So I was thinking about a Liskov substitution principle where you would want to have the same behavior in any of your instances of an abstract kind of concept. And here I think is the same idea which applies. If you are doing some abstraction and the real types on which you are working do not behave as modeled by the abstraction, then sometimes you would end up with different and unexpected behaviors. As we've seen, it's easy to create unusable interfaces in the sense that if you are respecting all the required preconditions, in the end you still get a result which is not necessarily valid, and there is no way, or there's no way to verify in a simple manner that whatever you obtained is good. I also put this idea that the documentation is part of the API. You cannot guess preconditions. The preconditions have to be clearly stated. Even if you are looking at the code, sometimes it's not clear what is required of you. So unless you actually have some good documentation for a library, it is not necessarily possible to write correct code using that particular library. And of course, I advocate for good, reliable, and portable libraries because writing portable code has a lot of challenges, and it's better to write it once and make sure that it works than everyone doing the same work over and over again. So thank you very much, and any questions?
Hi. Many years ago, I know that Microsoft published the SafeC library, which was actually intended for use to make C code better. And I believe that the philosophy there was that if you get arithmetic overflow or underflow, then it's a quick route to terminate, because that's obviously not what you intended. You think that's an adequate solution to the problem? I mean, you know what your types are, so it's not particularly adequate. But if you either have overflow or you don't. And if you do, then I'm not sure what you do about it.
Right. First of all, that would be Microsoft specific, and you would actually need to detect the error and not have the library terminate your program, right? And if you have good primitives, like which provide you the detection, and then, for example, for addition, if they could do addition with carry, then you could actually use this in a way that you can build larger constructs out of that. Yeah, so this is something which definitely is missing from that library. Mm. And I actually think that those are like some set of macros or something, and they were quite limiting in the types that you could put in there.
They were written for C, and I think it was part of the Trustworthy Computing initiative at the time. So, but very old. Thank you.
Thank you. So, thank you very much.